Okay, so we have a physics of fluids practice final exam, graduate level. This will be part one. Number one, let's go right into it. A compressible Newtonian fluid has density rho x comma t, velocity x comma t, pressure x comma t, and temperature xt. Part A, starting from conservation of mass in an arbitrary control volume, derive the differential continuity equation d rho dt plus del dot rho u equals 0. Okay, so for the equations here, starting with the continuity equation for part A, mass in a fixed control volume V, m equals the integral here, b of rho dv. Conservation of mass states with d dt integrated v, integrating the v bounds rho dv. That's going to equal this integral here, dv. So we have rho u dot nda. We're going to use the divergence theorem here. Okay, and from there, writing this out, this is going to be the integral of d rho dt plus del dot rho u dv equals 0. And since v is arbitrary, what we could say is d rho dt plus del dot rho u equals 0, or capital D sub rho dt. Capital D rho dt plus rho del dot u equals 0. Okay, so this is more of textbook derivation here for letter A. Okay, moving along, letter B. Using Newton's second law applied to a fluid element, derive the compressible Navier-Stokes equation. So here's what we have. All right. Okay, so let's see what we can do here for letter B. So letter B. Okay. Okay, so momentum equation for letter B. So momentum equation for letter B, let's see what we have. Newton's second law for a fluid element is rho du dt equals this del dot sigma plus rho g, where ddt equals partial ddt plus u dot del is the material derivative. It gives the rate of change following a moving fluid parcel. Okay, for a Newtonian fluid, we have this sigma equals this equation here with viscous stress tensor given here, this T sub ij. Okay, so these are our textbook equations. So for constant viscosity, we could say del dot sigma equals the following here. Some of this stuff I'm not going to read out just to go out, just to make this faster. Some of the computation isn't there here. And we have here writing the lambda equals that bulk viscosity zeta minus 2u over 3. That gives lambda plus mu equals that bulk viscosity there plus u over 3. And now this is going to yield rho du dt equals negative del rho plus u del squared u plus zeta plus u over 3 del quantity del dot u plus rho g. So pardon me anywhere where I may have misspoke. Take a look here. In this situation, that's our momentum equation here. And pardon me too if I happen to accidentally say pressure for momentum and momentum for pressure, because sometimes if I'm reading too fast, I'll read the P as a rho or a rho as a P. So my apologies for that. Okay, just follow the math is okay though here on the paper. But sometimes reading too fast visually, I say the opposite thing. My apologies. So here, C, what they want us to do for C. Okay, C, if we go back to the previous page, derive the mechanical energy equation. Okay, so we want to derive the mechanical energy equation by dotting the momentum equation with U. Okay, so mechanical energy equation. Okay, we begin with rho du dt equals this entire formula here. We're going to dot that with U. Rho U dot du dt is going to equal this right-hand side. Okay. And this is textbook stuff. That's why I'm just going over it quickly. This U du dt equals this. And we wind up with our rho d dt u squared over 2 equals this whole quantity here. Some of this stuff, a lot of words, but the symbols, I'm assuming you know what they mean. And you've taken this course, and this is more textbook stuff. So if we use identities at this point, negative u dot del rho here equals negative del dot rho u plus all of, basically, I'm not going to read out these identities because it's their tongue twister here. When we substitute these identities into our previous equation, we're going to get this rho d dt u squared over 2 equals this whole thing for the mechanical energy. So, and this is more, again, textbook stuff for letter C. Okay, so part D, under what assumptions does the incompressible Euler equation follow from the equations above? Okay, so here we have the incompressible Euler limit. So here's what we have. The incompressible Euler limit follows, okay, when we have this momentum equation with the rho constant, del dot u is 0, and the viscosity is neglected, mu equals 0. So the momentum equation is going to just become the following. It's going to be scaled down significantly. This rho times du dt plus u dot del u equals negative this side, and this plus rho g. So pardon me, I'm having a little bit of technical problems with the video, but part D, we just wind up with this for the momentum equation. Okay, and just be careful here because we're going to have pressure and momentum in a lot of these problems, and it's going to look like differentiating the rho from the u, from the p, pressure from momentum. Sometimes, if I'm saying it too quickly, it just gets conflated, but here's the math here behind it. So here's the math for letter D. Let's move along now to number 2. I think we're ready for 2. So that takes care of number 1. Because D, by the way, yeah, there's no E for that one. Pardon me, I didn't have a lot of coffee today. So, let's see. Alrighty. Number 2, a sphere of radius A moves through a viscous fluid of density rho and viscosity mu with speed u. Mu with speed u. Okay, the drag force is F sub d. Part A, using Buckingham pi theory, determine the dimensionless groups governing the problem. Okay, so dimensional analysis here. Here are variables, F sub d. We have rho, mu, u, and a. Okay, dimensions F sub d equals mlt negative 2. Rho equals ml negative 3. Mu equals ml negative 1 t negative 1. U is lt negative 1, and a is L. Okay, so we have 5 variables and 3 fundamental dimensions. So if we subtract 5 minus 3, we have 2 dimensionless groups governing the problem. Okay, all right. So from here, let's see what we could say. Just to let you know, as a segue to 2, show that the drag coefficient may be written as C sub d is F of RE, where C sub d is F sub d, over rho u squared a squared, Re equals rho ua over mu. Okay, so just adding on to this, for part B, if we choose rho, u, and a as repeating variables, we have one group here, pi 1, f sub d over rho u squared a squared. Another group is pi 2, rho u a over mu. Okay, so taking this into consideration, that we're going to rewrite these. Going on to the second page here. We're going to get this pi 1 equals c sub d, pi 2 equals Re, and c sub d equals f of Re, and some would define that c sub d as c sub d equals f sub d over 1/2 rho u squared a. Okay? Now, this differs by only a constant geometric factor. And the problem's definition is still valid here. Okay? Now, where is this from? This is a segue into part C. Okay? So, just going back to part C, it says suppose a laboratory model sphere is constructed at 1/3 scale. Determine how the fluid viscosity or velocity must change to preserve dynamic similarity. So, just taking that into consideration, if we go back to this differs by only a constant geometric factor. Sorry about the technical problems. The problem's definition is still valid. And for a 1/3 scale, we use a sub m as a sub p over 3, or a sub rho over 3. Dynamic similarity requires r sub em equals r sub ep. Okay. Now here's the thing. Again, be careful now. We have p's and rho's. Okay. And sometimes, again, if I'm reading too fast, I tend to conflate the p's and rho's, but the rho's are going to have, just to let you know, when I draw the p's, they're going to look like p's, and the rho's are going to look more like rho's. They're going to have like a wider circular portion here. So you could differentiate here what we have on the left and the right. We have this proportion. And if the same fluid is used, we have the following equations that we could use. All right. Now, since a sub m equals this quantity, u sub m equals this quantity, and also u sub m equals this quantity, u sub m is this, assuming the density does not change. So, moving in to part D, explain physically why flows with very different absolute sizes can behave similarly when Reynolds numbers match, that Re. So what we could say here is, from all this information, flows of different size behave similarly when Reynolds numbers match, because the ratio of inertial to viscous forces is the same. So we could say that Re equals the inertial effects divided by the viscous effects. Okay, so I know visually this is a bit strange, especially when you're involving pressure and momentum, but the math works out. And again, my apologies. I didn't have a lot of coffee today, so if I make a mistake with the verbal explanation, just know that the mathematical explanation, it works out. Okay, human error on my part. Okay, now moving along to number 3. Let's see what we could do with 3. Okay, so number 3. All right. So, consider an incompressible fluid with this velocity field that is given. Alpha and beta are constants. Okay, so vorticity. So this is a vorticity problem. So we're given this velocity field u. So U equals alpha x minus beta y, and V equals beta x plus alpha y. For two-dimensional flow, omega sub z equals dv dx minus du dy. Now, if we compute dv dx partial, we get beta. If we compute partial du dy, we get negative beta. Now, our omega sub z, that's going to equal beta minus a negative beta. That gives you 2b. So our omega is going to be 2 beta k hat. Okay, so that's our omega. That's what we need for part A. Moving along now for part B. Part B, we want to determine whether the flow is irrotational. Okay, so think about vector calculus here, flow irrotational. So here we have, for part B, the flow is irrotational if our beta equals 0. And what we're going to basically say, well, that's if our beta equals 0. Yeah, that's basically it. Now, for part C, we want to interpret physically the roles of alpha and beta. So what we want to do here is want to think about calculating the divergence. So we do that del dot u, du dx partial plus dv dy partial equals alpha plus alpha, gives you 2 alpha. So alpha measures planar expression compression, alpha measures planar expansion compression, and beta measures solid body rotation. And for incompressibility, what we need is that del dot u equals 0, and that alpha will equal 0. And so the given flow is incompressible only if our alpha value is equal to 0. Okay. Letter D, starting from the incompressible Navier-Stokes equation, derive the vorticity transport equation. Okay, and that was on the previous page. So what we're going to do in this situation, for the vorticity equation, we begin from the incompressible Navier-Stokes. So we have that Navier-Stokes. Okay. Find the curl. So finding the curl, we're going to employ these operations. I didn't put a lot of the computation behind it because just these are the steps. What's going to happen is when we do this, the pressure term vanishes because del crossed here with that del rho equals 0. So if we define omega as del cross with u, we're good to go with this using the vector identity for incompressible flow. We just wind up with this, and this is from vector identities. I'm not going to say the whole thing, it's there. Okay, and so what we wind up with when simplifying is our d omega over dt plus u dot del omega. That equals omega dot del quantity times u plus nu del squared omega. Okay. Part E, what they wanted us to do was explain the physical significance of the vortex stretching term. So the term here, omega dot del times mu times u, sorry about that, mixing up mu's and nu's, rho's and p's, is vortex stretching. Okay. It describes how stretching a vortex tube increasing its vorticity, similar to an ice skater, as an example, spinning faster by pulling in their arms. Okay, so that's a standard example there. These are canonical problems. Again, my apologies if I'm mispronouncing anything, but the math is correct on the paper. So, moving along to 4. Alrighty, so number 4. Okay, here's what we can do for number 4. A steady incompressible flow of the following speed. That's the free stream velocity, that u sub infinity, u infinity, free stream velocity, passes over a flat plate aligned with the flow. Part A, starting from the incompressible Navier-Stokes equations, derive the Prandtl boundary layer equations. Okay, so this is a laminar boundary layer problem. So for letter A, for steady incompressible flow, we have the following, and this is canonical. We'll let x be approximating L, y approximating delta. My apologies for the horribly drawn deltas. And mu approaching u, and then lowercase v approaching capital V. So continuity gives u over L is similar to v over delta, lowercase v over delta. So uppercase V is approximately u times quantity delta over L. And inside a thin boundary layer, our delta is much, much less than L. Okay, so what we have here, here's our x momentum equation. Okay, that u mu nu du dx plus v du dy. That equals negative 1 over rho, d rho looks like dx plus nu quantity, the sum of these second derivatives, partials here. This should be partial form in that d. Second partial of u with respect to x plus second partial of u respect to y. Okay, so this is the beginning of part A. We still have parts left of this. So from here, let's just read out the rest of the problem. We want to explain the scaling assumptions used in the derivation. We want to estimate the boundary layer thickness, delta of x, using order of magnitude arguments. And then we get to the wall shear stress, tau sub omega equals u du dy, evaluate y equals 0. That's mu. Show qualitatively why tau sub omega decreases downstream. In part E, explain the physical mechanism responsible for the boundary layer separation. Okay, so that's a lot. So I just want to get that out of the way before we move on to the second page here. So if you have that down, let's move along to the mathematics behind this. Okay, again, let's hope I could read this. I think so, hopefully. Continued. There's just a lot of variables. I couldn't find my glasses. That's why it's kind of embarrassing. I don't have my glasses on, so that's why sometimes I wrote small, just having some issues if I talk too fast, if I'm reading the variables properly. Quite embarrassing, but it happens. I'm human. So continued compare viscous terms. So we have this partial here. Second derivative of u respect to x. And this is going to be similar to u over L squared. Second derivative of u with respect to y. And that's partial. And that's going to be similar to u over delta squared. Apology again for the horribly drawn delta. Since delta is much less than L, we have u over delta squared is much, much greater than u over L squared. So the dominant viscous term is going to be nu, second derivative of u with respect to y, partial. So here we're going to wind up with a key formula. Partial derivative here with respect to x, partial derivative v with respect to y equals 0. And we're going to wind up with this equation as our sum equals that right-hand side, that negative 1 over rho dpe dx plus nu second derivative of u respect to y partial. All right. Now, what we could say here, just continuing with this, the pressure is approximately imposed by the outer inviscid flow. So partial here given is approximately 0. And for a flat plate with very uniform external flow, we get this partial is equal to 0. So this equation might look very familiar. We have u sub x plus v u sub y equals nu u sub yy. Okay, think about where that comes from. Alrighty, so moving along, boundary conditions here. Okay, u of x comma 0 equals 0, v of x comma 0 equals 0, and u of x y approaching infinity equals our u infinity. So we're going to estimate here delta x by balancing inertia and viscosity. Our u sub x approximates nu u sub yy. So we have u squared over x is going to approximate nu u over delta squared. So therefore, our delta squared approximates vx over u. Delta of x approximates square root of nu x over u infinity, or delta over x approximates re sub x negative 1/2 there. All read in symbological terms. So moving along to part D, the wall shear stress. That scales as T sub omega approximates mu u infinity over delta. Since delta increases downstream, T omega decreases downstream as well. Separation occurs when an adverse pressure gradient here greater than 0 slows the near wall fluid so strongly, okay, that du over dy y equals 0 equals 0, okay, and then reverses sign. Okay, so what we could say here, the physical mechanism responsible for boundary layer separation, we could say physically low momentum fluid near the wall. I was thinking of quantum mechanics, sorry about that. Physically low momentum fluid near the wall cannot overcome the increasing pressure. Okay. So again, the mathematics is correct. The ideas are correct. My apologies if I mispronounced any of the variables or whatnot. I'm just, okay, sometimes I'm on autopilot today. Not feeling too well, bit of a headache, but these things happen. Okay, and let's do number 5. This will be the last one of part 1. Number 5. Okay, number 5, consider incompressible irrotational flow past a circular cylinder over radius A. Part A, write the velocity potential for uniform flow plus a doublet. Okay, so part A, potential flow around a cylinder. For flow past the cylinder of radius A, the potential is the following. We have phi equals this u infinity quantity, r squared plus a squared over r times cosine theta. That's all for letter A, the velocity potential for uniform flow plus a doublet. That's all we need for letter A. For letter B, derive the velocity components in polar coordinates. So the velocity components are u sub r equals d phi over dr. U sub theta is 1 over r d phi over d theta. So we find respective partials. We wind up with this u sub r equals u infinity quantity 1 minus a squared over r squared cosine theta. U sub theta equals negative u infinity parentheses 1 plus a squared over r squared sine theta. So this is canonical. Both of these, A and B, are canonical. Part C, using Bernoulli's equation, determine the pressure distribution on the cylinder force. Okay, so here at the cylinder surface area, r equals a, u sub r, a, comma, theta equals 0, v sub theta, a, comma, theta equals negative 2 u infinity sine theta. And Bernoulli shows that following. This is the Bernoulli. Okay. And on the surface, we have u squared equals u theta squared equals 4 u infinity squared sine squared theta. Therefore, p of theta equals this entire thing here. All right. Again, we have pressure and momentum involved here. So here we wind up with our pressure distribution on a cylinder force. So this is pressure of theta equals this whole thing. Okay, and pressure is involved and momentum is involved. Those variables look very similar. All right. Okay, letter D. Show that the net drag force predicted by ideal potential flow is 0, D'Alembert's paradox. So the pressure force is in the x direction. It's proportional to the following integral. Okay, that's canonical. And what we could say is here, it's symmetric front to back. So the integral vanishes and d equals 0. This is D'Alembert's paradox. Okay. Okay. Now, from here, and letter E, explain why real fluids nevertheless experience drag. Real fluids have drag because viscosity produces boundary layers, separation, wakes, and irreversible momentum loss. Okay, so thank you, and please forgive me if I misread anything. Bit of a headache today. Don't have my glasses on, too, as a result. I'm going to do part 2, 6 through 10 next. So this is the end of part 1, and thank you again.